So, in the previous class, we have taken the introductory part of branch and bound, how the branch and bound is being evaluated has taken in the previous class. Today, we'd like to consider the first problem of branch and bound, the most probable problem which was already discussed by us in dynamic programming and the greedy method also, the knapsack. Here also the knapsack is so 0 by 1 knapsack only. No fractions are allowed here while placing the things here. So therefore, would like to take into consideration. Would like to take into consideration that the knapsack is going to be solved by using this particular problem. I mean this particular branch and bound problem. More specifically speaking, in branch and bound, we are trying to calculate. So we are trying to calculate using what is that? Least cost branch and bound. Okay. One moment, please. So more specifically speaking, we are trying to discuss this particular problem using the branch and bound of one of the techniques of branch and bound, that is least cost, LC branch and bound. Okay, how this could be done here? Let us have a look here. So we have to apply the least cost branch and bound technique on given knapsack. That knapsack instance, the maximum capacity of that particular knapsack is 15 units, and respective so weights and the profits of those objects will be, total number of objects will be equal to 4. Respective weights and profits of a given object will be seems like this. Okay, P1, P2, P3, P4 equal 10, 10, 12, 18, and the respective weights are 2, 4, and 6, 9. Okay, so based on this one, already we have known this particular problem. This problem is always trying to identify the decision making variables, something like so x1 comma x2 comma and so on. So these x1 x2 values must be xn up to xn, x2 x2 x3 and so on values must be so xi, where xi value must always 0 less than wait, there is no less than here because so everything will be must included or none of them has included here. So it may be include completely or none of them. 0 is equal to, so xi is equal to 1 here. If you want to consider one particular item, include completely. If you are not interested to take that particular thing based on the scenario, so don't include that. So if xi equal to 0, don't consider that particular item or that particular weight. Xi equal to 1, so ith element or ith weight is going to place into the knapsack. So that is the basic idea behind this one. Already we have seen what are the different criterions which we have to follow for the knapsack algorithm here. Okay. So for solving this one, so I'd like to take into consideration of least cost branch and bound here. This is very important to be considered here, least cost only. So actually branch and bound, least cost branch and bound will always suggest you, so consider that particular weight completely, otherwise none. None in the sense xi equal to 0. Completely in the sense xi equal to 1. There is no fractional part which is going to place into the knapsack. Fractional parts are not supposed to be entertained to place into the bag. Okay, so that is the first point which we'd like to consider while we are doing some kind of problem with the 0 by 1 knapsack with the least cost branch and bound. Then followed by second point we would like to perform. Already we have told that branch and bound problems are always perform only minimization problems. There is no information regarding to maximization, only minimization. But as far as the knapsack is concerned, it is maximized problem. Okay, branch and bound is suggested for only minimization problems. So branch and bound cannot be identified the maximization kind of things. But 0 by 1 knapsack is being always expected to have only maximization. Then how could you perform this one? How could you perform in the sense while performing this particular problem, all profits will be, so here we have given positive values. Here we have given positive values. These positive values will be converted into negative. If it is negative, minus 10 is very less value when compared to minus 2. Minus 2 is bigger value than minus 10. Minus 20 is less value when compared to minus 10. So based on that, minimization will be gets occurred when we have to take the values into negative, so that the maximization will be successful. So what exactly branch and bound is always suggested for solve the problems who are expecting the problems expecting only minimization. But knapsack is by default, the definition is concerned about this particular knapsack. Knapsack is always trying to get the output in a maximized range. Okay, to correlate these two, what kind of activity we are supposed to do here is all profits will be converted from positive to negative. After converting negative, so we would like to solve this particular problem. At the end, negative values will be converted into positive. Okay, then you could get the proper answer out there. So that is the point which we have to remember here. So look at this. To solve this particular problem, we have to convert the signs of profits into negative. It's very important point to be remembered. Okay, it is very important point to be remembered here. And as per the hypothesis of LC, least cost branch and bound, what exactly we are trying to perform? How you can explore the state space tree. So the node which does have least cost will be explored. The node which does have least cost will be explored further. If any node do have huge cost, then that could not be taken into consideration. So that is the point which we have to take into consideration while performing this particular problem using least cost branch and bound. Then, so to generating this state space tree, for generating this particular state space tree, so what exactly we are trying to perform here in the sense, we need to identify the upper bound. We need to identify the upper bound because the name itself is branch and bound. So we need to identify the upper bound. And what is the cost if you perform that particular operation at the upper bound? These two will be gets identified. These two will be always gets identified. Then how could you calculate that one? Upper bound will be gets calculated. So u equal to sigma I equal to 1 to n pi and into xi. So initially, we'd like to consider xi will be always 1 because initially we don't know which item is going to be selected until completion of the problem. We don't know what is the value. So therefore, to identify upper bound for every node, we'd like to consider xi equal to always equal to 1. While exploring, so xi value can be changed. While it is being exploring, while it is being drawing, explore in the sense, let us take one particular node. Explore in the sense there are two possibilities which we would have. So x1 will be equal to 1. So completely we have taken. X1 will be equal to 0. It doesn't take it. So this is what exploration. Then it will be forms two nodes, something like this. While exploring, xi value is known to us. But in the beginning, at a root node, xi value will be equal to 1. Xi value will be equal to 1 in the perception of root node. Okay, then exploration, yes, we would like to, so we came to know that what is the value of xi. I mean x1, x2, x3, x4 and so on. Okay, so that is the point which we have to take in. And here you are not allowed to take any fraction here. Fractions are so not allowed to take in while calculating this particular upper bound. Upper bounds are not supposed to take any fractions. Whereas the calculation of cost, same formula will be same, but fractions will be entertained in terms of cost. In terms of cost, so calculation of cost, fractions are allowed. But in the calculation of upper bound, because upper bound is related to branch and bound, cost will be related to one particular node, one specific node. So at so each and every node, yes, you can consider your cost. The cost must be in so with the fractions. With the fractions also, it is accepted. Okay. Now, initially, hope that you got this particular problem. The description of the problem here. So what exactly we are trying to perform here. Then we'll move to actual problem. So look at this. I have given entire problem here. This is the entire problem here, and I'd like to consider upper bound will be equal to, initially it is infinity. Initially it is actually it is infinity. After identifying the upper bound for each and every item, it will becomes to 32. Of course, we told that everything will be in negative. So look at this. So for upper bound, include one by one value so of profits. So actual profit, I mean actual weights will be, so weight of first item is 2. Look at this, weight of this one is 2. Weight of second item is 4. Weight of third item is 6. Weight of last item is 9. So 15 minus 2, that is 13 more units are remained. The second item, 13 minus 4, that is 9 more units are remained. So after that, 9 minus 6, so third item is 6. So that is 3 more items, 3 more units are remained. So you cannot fit this 3 more, within this particular 3 more units, you cannot fit 9 units here. So therefore, while calculating this upper bound, so we are not supposed to take into consideration of fractions. So therefore, fourth item cannot be placed. So consider that first item has been completely taken, second item has been completely taken, third item also completely taken. Fourth item, there is no space to fill complete fourth item. So therefore, fractions are not allowed. Still, fractions are not allowed at upper bound. So therefore, total profit will be this much: P1 plus P2 plus P3. That is 10 plus 10 plus 12. That is 32. Okay, initially it is infinity. So now upper bound value, so the upper bound value will be 32, so which is minus 32, cancel this one and apply minus 32 here. So that is why I have directly written here, that is minus 32. That is why we have written here. Okay, 32 for the upper bound value at node, I mean at root node. Cost will be, cost also be same, but fractions are allowed. Cost also be same, fractions are allowed. So look at this. So totally 9 minus 6, that is 3. How much amount of space is left over here? 3 more units are left over within the bag. So that the fourth item will be placed 3 by 9 into 18. 3 by 9 twos are 18. So 3 twos are 6. So therefore, that is the value 6. So partially fourth item has been placed. Partially fourth item has been placed. So therefore, you could say, so 3 by 9 into 18, so that is 6 totally, it will become under. So 10 plus 12, that is 32 plus 18, that is 6, 38. So lower bound, cost will be equal to minus 38, and upper bound will be equal to minus 32. For the first item, I have written everything clearly. For next item onwards, for next node onwards, I am not supposed to write it this much clear. Okay, I just calculate in a particular way. So for the root node, you need to identify what is the upper bound. Before going to identify the upper bound, so how could you place the items? You have to identify here. So if this is the order of what I call weights which are being placed into the knapsack, then the upper bound will be 32. If this is the order by inclusion of so fractions, if this is the order which you have to place, then cost of this one is 38. Now, to explore this one, so because we don't have any choices here, we have only one choice, that is node 1, which is root. No choices here. So let us consider if First item has been included into the knapsack. First item has been included into the knapsack. And the first item does not include the knapsack. There are two possibilities. There are two possibilities. First item has been included. First item has not been included. That is x1 equal to 1 or x1 equal to 0. Based on that, you need to also identify the upper bounds at node 2 and upper bound and cost at node 2, upper bound and cost at node 3 as well. So how this can be? So upper bound is, so far upper bound is 32 and this is actual our problem. So look at this, already we have this particular problem with us. We need to decide which node is being explored. Okay, we need to decide which node is going to be explored, whether it is 2 or it is 3. Let us examine. So if you want to take 2, so there is no change in terms of upper bound and lower bounds because previously we have identified the same. So therefore there is no change in cost and upper bound. So everything is same. But at node 3, item number 1 has not been included, but we have included item number 2, 3 and 4. So 2 can be placed completely, 3 can be placed completely. You can see 2 can be placed completely, that is 4. So 4 plus 6, that is 10. 10 plus 9, 19, which is greater than the value of knapsack. So therefore, fourth item cannot be placed in the calculation of upper bound. So second item, what is the weight of second item? 4 plus what is the weight of third item? That is 6 will be equal to 10 actually. How much amount of space which is required? Sorry, which is available with knapsack? Still more 5 units of space is available. Can you place within 5 minutes, 9 minutes can be accommodated? No, it is not accommodated. So we have to finish up the work here at that place. Now, cost will be, so first item has been placed completely, second item also placed completely, and rest of amount will be 5 divided by 9. And what is the cost? Profit of this one? 18 units the cost. So 9 twos are. So 18, 5 into 2, that is 10. So that is why 10 plus 12 plus 10, that is 32. Cost will be 32 and upper bound is, so that is 22 here. So take that particular value here. So here cost is 32 and upper bound value is minus 22. Look at this, which is minimum value when compared to minimum cost at 2 and 3. We do have a cost of minus 38 is minimum value when compared to cost minus 32. Minus 38 is lesser value when compared to minus 32. So therefore we have to explore this particular vertex. Because least cost is always trying to explore the cost which does have least at each and every node here. Now, at node 2, the cost is minimum. So therefore, explore the node 2. So here, if you explore the node 2, so how the particular values will be. So look at this. So at node 4, so okay, let me draw the node 4 here. Node 4 or node 5. Yeah, I have drawn here. At node 4, you can consider that x2 value has been included, or second item has not been included. First item has been included. We have decided that yes, first item has included. That is confirmed. Then we have to take into consideration of second item may be included, may not be included. So let us identify the cost and upper bound so that we will decide. So at node 4, so if you include x2, there is no change in upper bounds and cost. Same upper bound and cost will be there because item 1 has placed, item 2 has placed, item 3 has placed, item 4 cannot be placed. So cost will be 32. Sorry, cost will be 38 and upper bound will be 32, minus 32. Now at 5, at this particular place, we need to identify what is the upper bound and cost because one item, second item has not been placed. Second item's decision value is 0. So that we need to identify. 10 plus. So first item weight is 2. Second item is not being takes place. Third item weight is 6. So 6 plus 2, that is 8. 8 plus 9. Fourth item weight is 9. 8 plus 9 is 17, which is not supposed to be placed. So that is why we have taken first item and the third item profits. Fourth item has not been included. So therefore that is 22. 10 plus 10, 10 plus 12, 22. Now, so this is actually 8. 8 plus how much amount of space which is required, which is available here? So 7 more units are available. 8 plus 9, that is 7. 7 more units are, so 15 minus 8, which is 7. 7 more units are rest over. So 7 by 9 into, so 15 here, sorry, 18 here. So 9 2 is 18, 14 elements. So 10 plus 12 plus 14, that is 36. Okay, that is why you got 36. So therefore, here the values will be minus 22 and minus 36. When compared to these two elements or these two values, minus 38 is lesser value. So let me write minus 38 is less than, so minus 36. Yes, it is true. Since it is true, we have to explore the node 4 because it is bigger value when compared to 38. So explore node 4. Then already we have this particular data with us. Yes, this particular data is with us. So at node 4, so we have two more possibilities. What are those possibilities? Let me draw everything here, then you could understand very easily. Yeah. So there are two possibilities. So item 1 has been included completely. Item 2 has been included completely, and we have to decide that whether item 3 will be included or not. If you are supposed to consider x3 is equal to 1, there is no change. The values at node 6, minus 32, minus 38, or there is no change. But if you not include the value, I mean the item 3, not include the item 3, then what would be happen? So at node 7, look at this. At node 7, this is actually node 6. This is actually node 6. Node 7, item 3 is not included. Then what are the items which are left over? That is item 2. Weight of item 2 is 2 plus weight of item 1 is 2. Weight of item 2 is 4. And weight of item 4 is 9. So 9 plus 4, 13, 13 plus 4, 2. So totally it is 15. Yes, exactly. So exactly the knapsack capacity has been identified here. So therefore, upper bound will be 10 plus 10 plus 18, 38. Lower bound cost will be 10 plus 10 plus 18, that is 38 again. Look at this, 38. Okay, 38. So in this particular scenario, previously upper bound is minus 32. Actually, we have minus 32. Now, new upper bound has been identified, that is minus 38. So therefore, we have to cancel this one. We have taken minus 38 here. Minus 38 here. Then which item is going to be placed? Okay, next, which node is being explored? So look at this. Item 1 has been included. So at this particular place, let me take another color, then you could understand very clearly. Item 1 has been placed. If you place item 1, what is the weight? 2 plus item 2 has been placed completely. Then what is the weight? 4. So plus item so 3 has been placed. For example, if you are trying to explore node 6, item 3 has been placed. So that is 6. What is the value of this particular thing? 12. Is there any possibility to place next item? No, because if you place next item, it will be 21. Okay, 6 plus 4 plus 2, that is up to this one, it is 12. If you are supposed to place ninth, I mean next item weight, it will be goes to 21. So this particular thing, I mean exploration of this particular node is infeasible because you are not able to place the next item, next weight completely into the knapsack. So it is infeasible. You are not supposed to explore the node 6. That is what we have taken here. So which is exceed the capacity of the knapsack. So exploration of node 6 is infeasible, not possible to explore. So therefore, it could be infeasible and kill this particular node, and will be goes with 7. Explore node 7 here. Explore node 7 here. Okay. On exploration of node 7, what would be the specification? Let us see here. So this is the actual data with us. Up to this we have. Up to this we have. Now, let us go ahead and explore this one. At node 7, item 4 may be included or may not be included. There are two possibilities. Let me draw everything here. Yes, there are two possibilities. Look at this. There are two possibilities. You may be taken. You may be included this particular item. You may not be included this particular item. Then if it is included, what is the cost here in the sense? There is no change in the cost of node 7 and upper bound of node 7 at node 8 also. There is no change. But at node 8, so X4 is not included. X1 is included, X2 is included, X3 not included, X4 also not included at node 9. So therefore, so X3, X2 and X1 is included. Cost of, profit of the first node, first weight, and the profit of second weight is 10 plus 10, that is 20, 10 plus 10, 20. Here also same. Here also same. You can see the weight or upper bound of this particular value has been exceed the limit. Upper bound of this particular value has been exceed, because minus 38 is very lesser value when compared to minus 20. So therefore, kill this particular node. Kill this particular node. This is not supposed to be explored. And you can live nodes are 3 is live and 5 also live. Look at this. The weight of this one is. Upper bound value is minus 22. Upper bound value which does have with us is so minus 38. So when compared to minus 38, minus 22 is so maximum. So kill this one. Here also same scenario. Kill this one. Only one thing is available with us. This is at node 8. It has been available. So therefore, we need to choose the path based on this one. How could you choose the path here? This is the way you have to choose the path here. Look at this. The path will be taken in such a way. So x1 1 to 2, then followed by 2 to 4, then followed by 4 to 7, then followed by 7 to 8. 1 to 2, 2 to 4. Then followed by 4 to 7, 7 to 8. So that is the path which we have selected here. So look at this. That is the specific path which we have to select it. And here, as far as the decision-making variables, so here 1 to 2, the decision-making variable is x1 equal to 1, and 2 to 4, the decision-making variable x2 equal to again 1. Sorry, this is 1. Unknowingly I have written here this is 1. Then the value of 4 to 7, so x3 value equal to 0. The value of x4 at 7 to 8, x4 equal to 1. Finally, I equal to sigma I equal to pi xi, p1 x1 plus p2 x2 plus and so on. So 10 into 1 plus 10 into 1 plus 12 into 0 plus 10 into 18 into 1. So therefore, totally the cost will be acquired is 38. 38. Okay. In this way, we have to solve this particular problem. So finally, what exactly we are trying to identify here is every time at each and every node, you are expected to identify the upper bound and the cost. So which node does have least cost? You have to explore that particular node. Which node does have least cost? Yes, you have to explore only that particular node. Then the second node will be as a live node. After some time, those nodes will be get killed by the upper bound value. By the upper bound value, those nodes will be get killed. Okay, in this way, so using Knapsack, using the branch and bound, using least cost branch and bound technique, Knapsack will be solved in this particular way. Okay. So this is the problem, and go through. I will send you this particular video immediately to you after 20 minutes. I would like to send this particular video to you. So go through this particular video for one more time, then you could understand very easily. Okay. Just wait for a while. I'd like to take attendance of you. Attendance of you.
Ma'am, I application.